She did countdown. Need to get her one of those things, like the action,
Yeah.
But I have no audio to sync. I just record it as we go, so I don't need to do any of that nonsense. Let us begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students again, Lord. I just pray that you just bless this class, help us to understand the remaining ideas about contour integration, and I just pray that you be with us this week. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so excuse me. I'll try to keep the coughing to a minimum, but I make no guarantees. So I've showed you two of the fundamental examples in the technique of contour integration. The one we did was like integration of a rational function, which is in some sense typical. Basically you look at a complex integral which is kind of similar looking to the one that you're actually after, and then the complex function you integrate is just the one that restricts to the function you're interested in the integral of on the real line, and then you have this big half circle that goes to the integral of that piece goes to 0. That's kind of like the most I think classical example, the one that requires the least kind of perhaps ingenuity to think of. Well, I don't know. They're still kind of sneaky. But certainly the integral I showed you after that, right? Which isn't this one. Come on. So pretty much that would, anytime you have a quadratic function of a real variable where the denominator has at least, is at least degree 2 more than the numerator, then you can apply that idea we did last time, because the ML theorem will give you that the extension of the complex function to that half circle goes to 0. There's also a slight modification of that example, though, I should mention. Suppose you wanted to integrate something like a rational function times a cosine, or a rational function times a sine, right? If you just look at that, right, and replace x with z, then you'd have a function which is holomorphic except for where the denominator was 0, right? So, okay. But then the trouble is, if you just try to directly do what we just did up there, you'd get into trouble because cosine is like, it's unbounded as you go to that upper half circle, right? So that's not going to work. So a kind of a sneakier approach is needed. Instead of looking at cosine directly, you look at the exponential, because the exponential e to the az picks up cosine ax and sine of ax on the real line, and the exponential, right, is bounded. So where are we picking up on the video, Sharon? The whole screen? Okay, I guess that'll work. Thank you. Thank you. I want just this too.
All right.
No, I'm just kidding. Okay, so this function, e to the iaz over z squared plus 1, if you restrict that to the real axis, on the one hand it gives you cosine over x squared plus 1, but it also gives you, I times sine of ax over x squared plus 1. So it'll pick up the integral of sine and cosine divided by x squared plus 1 if we study the contour integral over that half circle going to infinity. And so basically the question is, where is the singular point of this function? Well, the exponential is holomorphic, so the only thing we ought to worry about, it's entire, right? The only thing we worry about is where the denominator is 0. The denominator is 0 at plus or minus I. So essentially, if we do this integral, over the half circle, if we do the integral over the half circle like this, right, counterclockwise. So the only thing we really got to worry about residue-wise is just I, because minus I is down here and it's outside, so Cochise residue theorem doesn't care about that. So that's what I do. I calculate the residue of e to the IAZ over z squared plus 1 at I use rule 3, which says I can do what? Differentiate, I take, how's it go? F of z naught divided by, I'm trying to remember what rule. G prime of z naught, yeah. So g prime is just 2z. And so you get e to the minus a, because I times I is minus 1 divided by 2i. So there's a residue. And then we apply Cochise residue theorem, right, to this half circle. And I mean, is it a half circle? It's not exact. It's a half circle plus a diameter. I mean, right? I mean, the diameter is part of it. So the diameter is the piece that's going to, as r goes to infinity, pick up the real integral. This piece is going to turn out to vanish by the ML theorem. And then, of course, what's over here is what it is. I mean, that's the result of the residue theorem. So here's the ML estimate, the modulus of e to the AIZ, e to the IAZ over z squared plus 1. Of course, this has modulus unimodular, right? This is modulus 1, and z squared plus 1 ends up being, if we can replace this with a smaller thing, r squared minus 1, supposing r is greater than 1, and there you go, as r goes to infinity, the ML estimate gives us that this integral is 2 pi r over 1 minus r squared, which goes to 0, so that piece drops out. So collecting our thoughts, we have, even though I started this discussion saying I wanted to integrate cosine over x squared plus 1, we have, whether we like it or not, calculated the integral of sine over x squared plus 1 as well. So this is equal to that because the other piece drops out, right, by the ML theorem. And so we have integral from minus infinity to infinity of cosine ax over x squared plus 1 plus I minus infinity to infinity sine of ax over x squared plus 1 dx equal to that. So what's the integral of sine of ax over x squared plus 1 from minus infinity to infinity? 0. Why is this not especially surprising? Yeah, because sine is odd, and odd over even is odd. And the integral of an odd function about a symmetric interval of the origin is 0. Now, you should be like, but wait a minute, my calculus 2 spider sense is tingling. I remember that this, right, that's the integral of an odd function. Do I need to turn on the lights, or do you think it'll get it? I got it, okay. So you might be tempted by the same logic. Okay, 1 over x is odd, right? 0. How do we define the integral from minus infinity to infinity is really the question, right? The standard definition takes the minus infinity infinity as separate, right? I mean, in other words, this is supposedly going to be equal to the integral from 0 to infinity, dx over x, plus the integral from minus, I mean, however you want to order them, dx over x. So you take the limit as the upper bound goes to infinity, you take the limit as that lower bound goes to minus infinity separately. And separately, those don't exist. Right? Well, I mean, or you could say that this goes to infinity and this goes to minus infinity. But infinity minus infinity in this sense is not 0. It's just, oh well. So what we're actually calculating here is not technically the integral from minus infinity to infinity. If you study this contour integration technique carefully, you'll see what we're actually calculating, the so-called principal value. The principal value of the integral from minus infinity to infinity of, like, you know, f of x dx, what is the limit as r goes to infinity of, like, the integral from minus r to r of f of x dx, okay? So the principal value, it symmetrically approaches infinity and minus infinity. It's the lazy thing you'd like to have done in calculus 2, but it's not the standard definition of integral from minus infinity to infinity. The principal value of an integral can exist even when the integral doesn't exist. The principal value of the integral from minus infinity to infinity of 1 over x is 0. Because for each r, the integral, well, oh, I'm sorry. There's still a problem here with this, isn't there? I would also need to define principal value for the, these are doubly improper. Well, how about 0 here? 0 is problematic as well, right? You have to approach 0 from the left and the right. But suppose you also approached finite singularities, like not at infinity but at a. If you have if a is an improper point in the integral, if you insist on approaching those symmetrically as well, that would be the principal value at a finite point. Like I approach the left and the right symmetrically. So for example, let's see here, how can I say this? I don't even want to write it down, it's too much writing, but you also need that idea in order to get this actually to work out to 0. So there's a little bit more than I really care to say in here about that. But truth be told, this is what I've really calculated is the principal value of both of these being 0. Now it happens to be the case that if the integral exists, it's equal to its principal value, right? If the integral doesn't exist, the principal value may still exist, okay? I think in this case, the integral does exist and it's 0 by a comparison test, right? Like I can bound this. This is less than or equal to 1 over x squared plus 1, right? But the integral of 1 over x squared plus 1 converges to pi over 4. No, converges to pi. We worked that out last time from minus infinity to infinity, right? So something that's larger than it integrates to a finite value, so this has to be finite. So the principal value is 0, and by the way, the integral also exists in 0. Okay. Excuse me. Last time we worked out some. So anyway, all I'm trying to say here, guys, is if you wanted to integrate basically any cosine or sine divided by a rational function, as long as it's quadratic or higher, you can follow the method of this example just the same. And you just have to look for all the zeros of the rational function and use basically the same argument. You can calculate the integral. Holy cow. I can take cosine or sine and divide by a rational function from minus infinity to infinity and just calculate the integral just by locating residues. That's really cool. I mean, if you think about it, that's wow. I'm not sure if I could do this integral we did last time just using, hardcore calculus 2, just like hand-to-hand combat, multiplying by cosine over cosine and partial fractions and some stuff. I might be able to do it. I don't know. I'm not going to try. This example is pretty because it breaks into 2 pieces. I'll let you read it. I'm not going to go over it. This brings us to our next topic. Excuse me. Integrals with branch points. So a lot of the functions we've looked at in here, we can define them to be holomorphic on a slit complex plane, right? Like the principal logarithm, for example. Holomorphic on everything except for the negative real axis, right? Or more generally, we can look at a complex power function like z to the a. We can get that it's holomorphic on the whole complex plane except for what? Except for like the origin modulo array, right? There's got to be some place where the argument function basically has to do that 2 pi jump, and that's just unavoidable for functions we construct one way or another with the argument. So it's a fact of life that we have to deal with these things, and it turns out if you use these so-called keyhole contours, something like this, or this, or this. Now this is what I would use for something that had, the jump on the negative real axis if my function naturally, and so sometimes you have to be a little bit creative which one you're going to use. Let me just look at an example here. Standard example. Suppose I want to integrate from 0 to infinity x to the a divided by 1 plus x quantity squared. All right. And here I'm thinking of a being between minus 1 and 1. Okay, not necessarily an integer. It could be 0.317, blah, 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 whatever. So the idea here is to study the integral of z to the a over 1 plus z squared. But z to the a, right? How do we understand that? We understand that in the complex domain in terms of how it filters through the principal logarithm. Or, as I've chosen to use here, I choose to use the logo. Sorry. The logarithm with a branch cut on the real axis, right? So basically the argument here goes from 0 to 2 pi. Right? Starts at 0 all the way over to 2 pi, that selection of angles. that selection of the argument. Any questions so far, Jagus? So this z to the a, defined by the modulus of z to the a times the exponential of a log cut on the positive real axis of z, this is holomorphic on the complex plane modulo the positive real axis, right? So what that means then is if I look at the function z to the a over 1 plus z squared, that thing is holomorphic on where? Well, that's holomorphic on the whole complex plane modulo the positive real axis and wherever the denominator is 0, which is just z equals to minus 1, right? So that's the singularity we have to worry about as we apply Cochise residue theorem to this so-called keyhole contour. Yeah, words. My computer will be hungry soon. I should feed it. All right, there we go. All right, so do you guys understand the preamble here, what we're doing? Okay. I mean, honestly speaking, these problems aren't that hard. They're kind of lengthy. All right, there's a lot going into them. But once you understand the narrative here, I think you can do them too. It's just a matter of persistence, right? Okay, so so I got oh, come on. So I do some name calling here, right? I give labels. L plus is this piece. Gamma R is going to be the outside. What?
Yeah, I understand. Yeah.
What is that? No. Okay, so counterclockwise, I want this whole kind of, biting Pac-Man, or whatever you want to think of it as, to be. So this should go this way. All right. So that's right. That's right. That's right. This is an anathema. Remove that. Oh, awful. Good gracious, what am I doing? Oh. Okay. I need to cover that up somehow. It's just unfortunately, everything I cover it with, it'll just project onto. Tempting. Don't give me ideas. Okay, so the point is gamma R goes counterclockwise like that, but then gamma epsilon goes clockwise because it's basically it's an inside one, right? See that? And then L plus goes this way, L minus goes this way. L plus and L minus are reversals, but they're not quite accurate. They're not quite reversals because they're not exactly the same point set. The one is a little bit above the x-axis. The other one's a little bit below the x-axis. That's really important because that means the argument, right, theta on L plus is 0. Theta on L minus, I believe, is 2 pi. Okay, big difference. Okay, technically it's really, really close to 0, and it's really, really close to 2 pi, but let me just say it's 0 and 2 pi. So I need to calculate. Then I can apply Cochise residue theorem to this keyhole contour, right? I mean, to this whole region. So again, it's just the region inside this piece right here, right? So the only residue there is at -1. So I need to calculate the residue there, and I do so with the usual technique. I do what? Well, it's a double pole, right? So I'll use rule 2. I multiply by, I clear out the pole, multiply by 1 plus z squared, and then I differentiate and plug in z equals to -1. So the derivative of z to the a is a times z to the a minus 1. Plug in -1, I get a times -1 to the a minus 1, also known as minus a times e to the I pi a. All right. So to collect our thoughts then, what we have is we've got Cochise residue theorem applied to that contour up there. We've got the gamma r integral, we've got the L minus integral, we got the gamma epsilon integral, and we got the L plus integral. Now the gamma r and the gamma epsilon, these pieces are going to go to 0 by an ML theorem again, but different reasons. The R1 is going to go to 0 as R goes to infinity. The epsilon one is going to go to 0 as epsilon goes to 0. So that's what we're going to do, is we're going to imagine pinching the keyhole down to a point and letting the outside circle go to infinity. As we do that, the L plus and L minus become basically from 0 to infinity and from infinity back to 0 again. But again, with different arguments in that limit. So basically, this is the estimate for the gamma R. This is the estimate for the inside little circle. Of course, when we multiply by the length of the circle, we get this times 2 pi r. But if r is greater than 1, that limits to 0. Let me go down here. Okay, so, well, be careful. Be careful, be careful, be careful. I get 2 pi r to the a minus 1 over this. Now, as r goes to infinity, this, of course, goes to 1, right? But how about this? This only goes to 0 if what? If a minus 1 is less than what? I need that that's less than 0. Otherwise, I don't really have a reciprocal power of r. Like, for example, if a minus 1 is equal to 0.5, that would be like 2 pi squared of r. As r goes to infinity, that goes to infinity. So I need that this r, the exponent here, has to be less than 0. Right? If that's the case, then this goes to 0. So that's why I need the condition that a minus 1 is less than 0 for this integral to vanish. For the other integral to vanish, I actually need the opposite kind of thing. I need that a plus 1 is greater than 0. Otherwise, this won't go to 0, right? If a plus 1 is like 0.5, excuse me. If a plus 1 is less than 0 here, then that would be like a reciprocal of epsilon. Then as epsilon goes to 0, it would diverge. So I need a non-negative power. Actually, I need a positive power. Otherwise, if a was 0, if a plus 1 is 0, then I'd have it just goes to 2 pi, which would also be troubling. Right? I want this to go to 0. So I need a plus 1 as a condition for that. So in total, you see we need the condition minus 1 is less than a and 1 is greater than a if you put these two together. In other words, the absolute value of a is less than 1 is the condition we need for both of these contours to simultaneously vanish by an ML argument. So in the limit as epsilon goes to 0 and r goes to infinity, the L plus integral becomes the integral from 0 to infinity of this divided by that. Notice that the argument here, what about the the function again we're integrating is, what was it? E to the az over z plus 1 quantity squared, right? And so this just goes to e to the ax over x plus 1 squared, right? Oh, I'm sorry. I'm still not right. It's not this, is it? It's z to the a, right? Sorry. It was z to the a, and so this just goes to x to the a for the L plus with theta equals to 0, but the other one it goes to e to the, what is it? 2 pi ia times x to the a over x plus 1 squared for theta equals to 2 pi on the L minus, if I got it in the right order, I think. Yeah, for L minus, that minus, what is that minus from? Oh, that's because L minus goes back to the picture. In order to get from 0 to infinity, I need to reverse it, right? See, L minus goes from infinity to 0, so if I want to go from 0 to infinity, I put a minus. And then the 2 pi ia, this is what z to the a restricts to on L minus, given our choice log with the cut at 0, okay? So they're different. L plus and L minus are not the same integral. They differ by a phase factor. This is really the most important aspect of this whole example, is that presence of that phase factor. as a consequence of the jump of the logarithm, right? So putting it all together then, in the limit epsilon goes to 0 and r goes to infinity, we have integral of x to the a over 1 plus x quantity squared from 0 to infinity minus 2 pi I a, integral from 0 to infinity of x to a over 1 plus x squared dx. Of course, what we're actually after is that integral, so solve for it. Solving for the integral gives us minus 2 pi I a e to the I pi a, which came from the residue earlier in Cochise residue theorem, and divided by this. And then you just massage it a bit, and you can see that that's actually pi a over the sine of pi a. And that calculation works for the modulus of a being, well, the real part of, we had it for the absolute value of a between minus 1 and 1. And so Gamelin points out that because that function is holomorphic on the strip, real part of w between minus 1 and 1, you can extend this result onto that strip just the same. In other words, if I can replace a with like w as long as the real part of w is between minus 1 and 1, and this is still a true result for that complex power. I don't really care too much about that. I'm mostly interested in this real integral. So, but there you go. That's an example of a typical keyhole contour type integral. Basically the song and dance here is you pick a branch and integrate around it. That's pretty much it. Here's another example, but it's the same story. This time, and I guess typically we use the branch cut from 0. I mean, I usually kind of use the same one. This one uses the same keyhole again because it's just natural to use the cut at the positive real axis, because that way like the L plus and L minus curves pick up the integral from 0 to infinity. And then the same thing with a phase factor. So once you do one of them, it's kind of hard to stop. They're addictive. So there's another example. But I've broken the addiction for today, so let's go on here. Where was I? Fractional residues. Fractional residues, kind of wacky. Basically, the idea here is if you have like a curve, right? And maybe on the edge of the curve you're looking at, you've got a function which has a singularity, right? If you take that and you put a little bubble around it, and you kind of look at the curve and the limit that sort of little arc. So I need to draw a picture. So something like this. Suppose this was a singularity for f of z. If you do something like this, suppose you have a curve like that, all right? And then, I don't know, whatever else, who knows what happens anywhere else, whatever. So maybe you've got some singularities in here, z1, z2, z naught. So if you apply, basically there's a Cochise residue theorem here, which says that the integral around this curve, whatever it is, the boundary of d, of f of z dz, it'll equal the residue. Okay, so you'll get, you'll get 2 pi I, residue at residue of f at z1, and then, plus the residue of f at z2. Fine, the inside ones, the usual song and dance. But then plus, now here's the funny thing, 2 pi divided by the theta, let's say theta naught, well, let's say change in theta, times the residue of f of z at z naught. That's the way it works. So basically, if you pick up on some singularity, which is right on the edge, and you take the limit of the contour as this kind of shrinks down to the point, in that limiting sense, it does contribute to the integral in this way. When so like change in theta is precisely, if you kind of this angle right here. I better turn on the lights for a second. Thanks. So this is the fractional residue. It says that if you take some kind of contour with some kind of edge singularity and you approach it, think about the limit of a family of contours, really, where you're squeezing down on that singularity. Then you pick up part of the residue from that singularity. Exactly how much is geometrically corresponding to the angle subtended there. Simple case, if you have a line, right? If you have a line and you have a singularity on the line, if you integrate along that line, taking a little half circle around the singularity and squeezing the half circle down on the point, then you pick up half the residue, because the theta is pi. The change in theta is pi, and 2 pi over pi gives you 2. Wait a minute, 2 pi over... Yeah, just 2 instead of... Is that right? Oh, duh, sorry. Okay, anyway, let me turn the lights back on and look at the theorem. The way this is derived, I mean, this is kind of a, I mean, when I see this theorem, I'm like, oh my goodness, how am I going to prove that? Like, how do you prove that? The answer is easily. It's a stupidly easy result. So here's the idea. If you have a simple pole and C epsilon is the, so basically just focusing, this theorem just focuses in on just the little arc. It's basically just this piece right here. Because once you have that, you can kind of adjoin it to the rest of the things and get the thing I'm claiming over there. But so the integral over, as epsilon goes to 0 of the arc of radius epsilon, f of z dz is just alpha I residue of f of z naught, where alpha is the angle through which you go in the arc. So when the angle is 2 pi, you get the whole arc. Or you could think about wrapping around more than once, and then you'd get multiple counts of the residue, as we'll talk more about next class. Well, I'm not sure it can be called a class or not anyway, as I will share with you via the YouTube. Stupid jerky. Anyway, so basically here's the deal. If we have a simple pole, you have this Florid expansion, right? So g of z is analytic. So as epsilon goes to 0, whatever the integral is of the analytic function along the little arc, it's basically proportional to the arc length. As the arc length goes to 0, that piece drops out. Make sense? Because if it's analytic, it's bounded on the little arc. So we can neglect that piece. The only thing that matters is the singular piece. And when you integrate the singular piece along the arc, you just put in the parameterization, epsilon e to the I theta, from theta naught to theta naught plus alpha. You get this, the e to the I thetas cancel, and you're just left with the integral of 3 theta, and there it is, which is just I alpha times the residue. Man, that's simple. I love this little proof. Here's a typical application of that. Suppose you wanted to integrate this thing, right? dz over z plus 1 times z minus I. So if I look at an integral which is along the real axis, I have a problem at minus 1, right? Because that's a singularity which is on the real axis. So in order to understand such an integral in a meaningful way, we encircle the singularity with a little half circle and take the limit as we approach it. That's, in some sense, sort of a generalization of the notion of an improper integral, where you have a singularity on the edge of the integral. That's the meaning. Okay, so anyway, I use the theorem. This means I pick up half the residue, right? So instead of having 2 pi I have pi I. And also, why is it minus pi I? See, it's clockwise. It's a little, so I mean, you could think of alpha being minus pi there. So it's minus pi I times the residue, which works out to pi times 1 plus I over 2. And then, excuse me, let's see, the other singularity for this integrand is at I, which would be up here somewhere, right? So if I apply Cochise residue theorem to this, so gamma, let's say gamma is this whole thing, right? Gamma is the whole thing. If you take r going to infinity, you're always going to enclose just the singularity at I, and you also have the half singularity on the lower edge, right? The half singularity on the lower edge gives us pi times 1 plus I over 2. Cochise residue, the residue, what's the residue at I? Did I calculate that anywhere? I'll get around to it eventually. Oh, down here. Why minus I? What? Oh, that's a typo, guys. I don't know what to do. I know, what idiot wrote these notes exactly? Okay, you didn't say idiot. I inserted the idiot, but I also inserted the idiocy here. So let's see here. That should be a plus I, obviously. All right, anyway, so did I actually follow through on that error, or is that just a typo? This is a simple pole, right? So the way to calculate simple pole, multiply by the corresponding factor and then take the limit. So yeah, I did. Dang. That should be I plus 1. Oh, man. I should have. Hopefully I made an even number of errors here. We'll find out soon. 2 pi I. I think that should be I plus 1, unless I'm missing something here. So to rationalize that, I do 1 minus I, 1 minus I, and that gives me 2 pi I plus 1 over 2. So that's pi times 1 plus I is what I should get from that, I feel like. Oh, yeah, I made that error. I'm sorry about that. I got to fix these. Anyway, that error aside, I hope you understand what we're doing. I mean, do you get the bigger idea here of this example? So I'm not super confident about the answer here, but you see anyway, at least you see the technique here. So if we want to integrate something that has a singularity on the edge, then we can encircle it with like a half a circle or something. Take the limit. Example 7.5.3. There's dangerous aspects to that. I'm going to skip over it. I covered the example natural log from 0 to infinity, natural log of x over x squared minus 1 in lecture. That's on page 210 of Gamelin. Huh. That must be from another semester. Let's see here. What's this here? So here I'm talking about principal value again. Here's yet another example of an integral of a rational function. Here, x squared over x squared plus 6, x to the 6 plus 1. Now, x to the 6 plus 1 has singularities at the 6th roots of minus 1, right? So you got to think about these 6 points to calculate then. Going back to what we started with today, you'd have to calculate the residue here, here, and here, add them together. You apply the ML theorem, this piece goes to 0. This piece gives you the integral from minus infinity to infinity, rather the principal value thereof, and that's this example. So I don't know why Gamelin gets around to talking about principal values pretty late in this chapter. I really feel like principal values should be at the start of the chapter and should be woven throughout the whole discussion, and yet that's just not the choice he made. And then I followed his book, so, oh well, I can blame him, I guess, but there's really not much to blame. It's just a minor little jibber jabber. Anyway, so you calculate those 3 residues and out pops pi over 6. It's kind of fun, but I mean, you could spend a half hour going over this example. It's an interesting example. Then Jordan's lemma is the next and the last bit of our story for this semester, at least. It says that if you have a semicircular contour of radius r in the upper half plane, let's say, then, well, it's a half circle, semicircular, right? So 0 to pi. Then the integral over that half circle of the modulus of e to the I z dz is less than pi. The proof of this is a little bit technical and not really the point of what I'm talking about, so I'm going to skip over it and show you how we use this. So, integral of sine x over x. See, that we couldn't do with our previous methods because the ML theorem breaks down in this example. If we just try to do straight ML, then we'd end up with like basically 2 pi r over r here. And so that wouldn't naturally, I mean, we've always had 1 power of r upstairs and at least a quadratic downstairs. So we ended up with like 1 over r squared, 1 over r cubed, something like that for the rational integrals, right? So this defies the simple ML arguments, but the Jordan lemma I just glossed over gets it for us. So here's the way it goes. This integral, right? So basically we have two pieces. The one is the integral from minus r to r. That's going to actually pick up the integral from minus infinity to infinity as r goes to infinity. That's the piece we're most interested in. The singularity at 0 is harmless. It's a removable singularity, as we hopefully are starting to understand from homework. No, it's okay. And then we're hoping that the integral along the half circle, the CR, is just 0. Let's see why. So the modulus of this is less than or equal to the modulus of e to the I z over z dz by the ML theorem, supposing that it exists. But it exists because we have, well, okay, what's the modulus of z on the circle of radius r? It's just r. So that pulls out. But then this is exactly what Jordan's lemma told us is less than pi. So then we get pi over r. Voila. As r goes to infinity, this goes to 0. And so the integral from r to goes to infinity of integral from minus r to r of e to the ix over x, which is, e to the iz over z on the real axis, that. And then I have to do what? Minus pi I, this residue, the residue at 0, which I don't think is especially exciting because I think that that's a removable singularity. Well, is that? Oh, but we're not looking at just the sign, right? We're looking at the exponential sign as piece of it. So it's true that the sine x over x has a removable singularity here, right? Cosine of x over x does not have a removable singularity here. Cosine of x over x has a simple pole at 0, right? So that's interesting, and that's why this piece has something to say. And then, of course, this piece we just showed is 0. So using the half a residue theorem, in fact, this is kind of interesting because all of the integrals coming from the half residue. There is no singularity of e to the iz over z inside the half circle, right? It's just the edge singularity that's contributing. Excuse me. So we get then, this works out to pi times I. Actually, excuse me, this residue is just 1, so when you add it to the other side. I mean, that's obvious that the residue of that's 1, right? E to the iz over z is what? 1 plus iz plus dot over z, which is 1 over z plus I plus dot holomorphic. Residue is 1, right? Obvious. So the residue of e to the iz over z at 0 is just 1. And there you have it. And then we break this into the cosine and the sine by Euler's formula as usual. And that gives us that the principal value of the integral from minus infinity to infinity of sine x over x is pi, whereas the principal value of the integral of cosine x over x from 0 to infinity is just 0. There are yet weirder There are even weirder contour integrations. I mean, this stuff is endless. I mean, there's so much more than I've showed you, all right? But I think what I've shown you is a pretty healthy introduction to it. If you want to learn more, you can read more for sure. The one thing I might cover some other semester that I didn't get to this semester was, well, there's a couple things actually. The one is the exterior. Sometimes they'll look like a dog bone contour. They have like a pair of singularities or something that kind of like draw like a little dog bone around it. And then the thing you're integrating over is the exterior of the dog bone. So these integrals over exterior domains, they're really wacky. The other thing that's interesting, and we might get back to this another day, is you can turn this around and you can look at other examples where, like this is later in my notes, something like this result is very interesting. This Mittag-Leffler stuff. Here, you end up using contour. You do contours over things where you have not just one singularity, you have infinitely many of them. And so the residue calculation ends up getting connected to a particular series of things. And so you can actually use residues to make contact with certain series calculations, which is another very interesting. Maybe I'll spend a day on that after break, maybe. We'll see. I mean, I have to decide. The Mittag-Leffler material is very, very interesting. It's kind of partial fractions on steroids in some sense or another. It's deeply interesting, and then infinite products. Well, I probably won't get to that this semester. Sorry about that. But you can read my notes. See what we did last time. There's that Weierstrass product theorem you're interested in there, Nathan. See, there it is. Anyway, so again, I have jury duty next time. So what I'm going to do is I will make a little video where I work through the notes on the logarithmic integral and Roche's theorem. It's very, very simple material in some sense. Basically, what it says is that you can figure out the number of zeros and the number of poles a particular meromorphic function has inside some region if you just study the argument of the function as it goes around the region. For example, if you look at z cubed plus 1, right? Z cubed plus 1, if you look at that function as you go around to, say, a circle of radius 2, you'll see that the argument goes through 6 pi. That corresponds to the fact that there are 3 zeros of z cubed plus 1 inside the circle of radius 2. So it's a very sneaky way of locating zeros and poles just by studying the argument of functions around some bounding curve. It's a kind of dark magic. And it also gives us finally really a constructive proof of the fundamental theorem of algebra. So that's what you have to look forward to. Hopefully we'll have that video posted so you can watch it Wednesday in the comfort of your own apartment or whatever. I will not be here Wednesday.
Are you going to have the quiz posted and or a list of proofs we should know?
Yes, I should have the quiz posted and or a list of proofs by Friday. What's that?
Hopefully and not work. Or just no quiz?
No quiz? I think the quiz is helpful. So anyway, thanks guys.